Somewhere inside a university lab in Chicago, a small team of physicists quietly solved a problem that has haunted quantum computing for almost 30 years. They didn't build a faster chip. They didn't discover a new particle. They found a shortcut, a way to cut the number of qubits a working quantum computer needs by 10 to 20 times. And if that number holds up at scale, it could move practical quantum computers from decades away to within reach, faster than almost anyone predicted. Stick with me, because by the end of this video, you'll understand exactly what they found, why it matters, and why some of the smartest people in this field are still telling you to be careful about how fast this moves. Let's start with the problem itself, because without it, none of this makes sense. A quantum computer doesn't store information the way your laptop does. Your laptop uses bits, simple switches that are either off or on, 0 or 1. A quantum computer uses qubits, and a qubit can exist in a strange in-between state, a mix of 0 and 1 at the same time. That's what gives quantum computers their power. They can explore many possibilities at once instead of checking them one by one. In theory, that means a large enough quantum computer could crack problems that would take a classical supercomputer longer than the age of the universe to solve. Things like simulating new drugs at the molecular level, designing better batteries, or breaking certain types of encryption. But here's the catch, and it's a brutal one. Qubits are almost unbelievably fragile. Imagine trying to balance a pencil perfectly on its tip, on a table that's constantly vibrating. That's roughly what it's like to keep a qubit stable. Stray heat, tiny electrical noise, even a cosmic ray passing through the room can knock a qubit out of its delicate state. Engineers call this decoherence, and it happens fast, often in millionths of a second. So the moment you try to do real, useful computation, errors start piling up. The fix scientists came up with decades ago is called quantum error correction. The idea is simple to describe, even if it's brutally hard to build. Instead of trusting one fragile qubit to hold a piece of information, you spread that same piece of information across many physical qubits, so if one of them fails, the others can catch the mistake and fix it. This bundle of physical qubits working together to protect one reliable unit of information is called a logical qubit. And logical qubits are what you actually need to run useful programs. Here's where the real trouble starts. The most widely used error correction method today is called the surface code, and it works, but it's expensive. Extremely expensive. To create just one dependable logical qubit using the surface code, you often need hundreds, sometimes over 1,000, physical qubits standing guard around it. Now multiply that by the number of logical qubits an actually useful quantum computer would need to do something like break modern encryption or simulate a complex molecule, and you're suddenly talking about needing millions of physical qubits. Not thousands, millions. Today's best quantum computers, from companies like IBM and Google, are working with a few hundred to a couple thousand physical qubits total. So you can see the size of the gap. This is the wall that has kept quantum computing in the promising but far away category for years. And it's exactly the wall the University of Chicago team decided to attack. The breakthrough came out of the Pritzker School of Molecular Engineering at UChicago, led by Professor Liang Zhang, with graduate student Qian Xu as the lead author on the original blueprint. Their idea wasn't to make qubits less fragile, it was to make the error correction itself dramatically more efficient, using a completely different mathematical structure called quantum low-density parity-check codes, or qLDPC codes for short. Think of the surface code as a security system where every guard can only watch the guard standing directly next to them. It works, but it needs an enormous number of guards to cover a large area. qLDPC codes are like giving each guard the ability to radio any other guard anywhere in the building instantly. Because information can be checked and corrected across long distances instead of just next-door neighbors, you need far fewer guards overall to protect the same amount of information. The problem is, this idea isn't new. Scientists have known qLDPC codes were mathematically more efficient for years. What stopped anyone from using them was hardware. Real quantum chips, especially the superconducting kind IBM and Google use, wire their qubits in fixed positions, like seats bolted to the floor. You can't just have any qubit talk to any other qubit across the chip. The physical wiring doesn't allow it. So this elegant, efficient code existed on paper, but nobody had hardware flexible enough to actually build it. That's the piece the Chicago team paired it with, and it's arguably the more surprising part of the story. Instead of using traditional superconducting circuits, they built their blueprint around reconfigurable neutral atom arrays. Picture a grid of individual atoms held in place, not by wires, but by tightly focused beams of laser light, acting like invisible tweezers. And here's the key part. Those laser tweezers can physically pick atoms up and move them to new positions in the grid, mid-computation, connecting qubits that would otherwise be far apart. It's less like a computer chip and more like a chessboard where the pieces can rearrange themselves between moves to make new connections possible. Suddenly, the any guard can radio any guard idea wasn't just theoretical anymore. It was something you could actually build. When Zhang and Shu's team combined the two, the qLDPC math and the movable atom hardware, the results were striking enough to get attention across the entire quantum computing field. Their blueprint suggested you could bring the number of physical qubits needed for large-scale, fault-tolerant quantum computing down from the millions the surface code demanded to somewhere in the tens of thousands. That's not a small improvement. That's a 10 to 20 times reduction in the raw resources needed to build a genuinely powerful quantum computer. And unlike a lot of quantum computing headlines you might have seen before, this wasn't just a hopeful prediction. It came with detailed engineering calculations showing how the atoms would need to move and how few control lines the system would actually require. But this was still a blueprint on paper. The real test was whether anyone could make the numbers hold up in an actual physical experiment. That test came later, and it came from an unexpected direction. In early 2026, a separate but closely related team, researchers from QuEra Computing, Harvard, and MIT, working in the same reconfigurable atom array space Chicago's blueprint had opened up, pushed the idea even further. They demonstrated codes with encoding efficiency above 50%, something previous high-rate qLDPC attempts had never managed at a realistic size. To put that in plain terms, more than half of every physical qubit they used was going directly toward useful information, instead of being burned on overhead. And the reliability numbers were almost hard to believe. For a setup using around 1,100 physical qubits to encode roughly 580 logical qubits, they measured a logical error rate of about 2, 9 times 10 to the negative 11 per correction cycle. Scale that up to about 2,300 physical qubits, and the error rate dropped even further to roughly 1, 3 times 10 to the negative 13. Researchers have a name for reaching this kind of astonishingly low error rate. They call it approaching the teraquap regime, a rough threshold associated with running the kind of large, complex algorithms that would actually be useful in the real world. There's an important honesty check here, though, and it matters more than the flashy numbers. The team behind that 2026 study was direct about what they had actually proven. In their own words, shared publicly by QuEra, this was, quote, a quantum memory result, meaning they showed that information could be stored with extremely low error rates at high efficiency, but full computation, actually running logical operations on that stored information, still needs further work. As they put it themselves, memory is the foundation. If a quantum computer can't hold information reliably, it can't compute reliably either. That's a crucial distinction because storing information safely and actively computing with it are two very different engineering challenges. One is like proving you can keep a message locked safely in a vault. The other is proving you can open that vault, do complex work with the message inside, and lock it back up again without anything going wrong. This research nailed the vault. The next chapter is about what happens once you open it. And remarkably, we didn't have to wait long to see the next chapter start unfolding. On July 30th, 2026, IBM and researchers from the University of Chicago announced a new demonstration that pushed things one step closer to real computation. Using a new error correction method, they encoded 70 logical qubits and used them to solve a problem specifically chosen because it would be effectively impossible for even the most powerful classical supercomputers to simulate directly. Their quantum system completed the task in around 15 minutes. 70 logical qubits might not sound like a huge number, but remember, under the old surface code approach, protecting that many logical qubits could have realistically demanded tens of thousands of physical qubits on its own. This was one of the largest demonstrations of logical quantum computing to date, and just as important as the speed, the team built in a way to verify the results were actually trustworthy, not just fast. Bill Pfefferman, an associate professor at the University of Chicago involved in the work, put it plainly, verification remains one of the biggest challenges in firmly establishing real quantum advantage. In other words, it's not enough for a quantum computer to be fast. You have to be able to prove it got the right answer, and proving that has historically been just as hard as the computation itself. So where does all of this actually lead? Let's talk about what's really at stake here, because this isn't just an academic curiosity chasing bragging rights. If the number of physical qubits needed for fault-tolerant quantum computing really can shrink by 10 to 20 times, entire timelines shift. Drug discovery is one of the clearest examples. Simulating how a new molecule will actually behave inside the human body is a calculation so complex that classical computers have to approximate it, often imperfectly. A sufficiently powerful quantum computer could simulate these molecular interactions directly, potentially cutting years off the process of discovering new medicines. Material science faces a similar wall. Designing better batteries, more efficient solar cells, or room temperature superconductors all involve modeling atomic interactions that are, again, extremely difficult for classical machines to handle accurately. Then there's the topic that tends to make people the most nervous, cybersecurity. Much of the encryption protecting your bank details, your medical records, and government communications today relies on math problems that are essentially impossible for classical computers to solve in a reasonable amount of time. A large enough fault-tolerant quantum computer could, in theory, break some of that encryption. This is exactly why governments and companies around the world have already been racing to roll out what's called post-quantum cryptography, new encryption methods designed to resist quantum attacks, even before large quantum computers exist. So no, this breakthrough doesn't mean your bank account is suddenly at risk tomorrow. But it is one more sign of why that transition to quantum-safe encryption is being treated as urgent rather than optional. Now, before this starts sounding like quantum computers are right around the corner, let's pump the brakes for a moment, because that's exactly the kind of overconfidence that has burned this field's credibility before. Experts differ quite a bit on how fast we get from these lab results to something you or I would recognize as a genuinely useful quantum computer. The 2026 memory demonstration, as impressive as it was, still needs to be extended to full logical operations. Decoding, the process of figuring out exactly what went wrong and fixing it in real time, has to run fast enough to keep up with actual computation. And researchers themselves admit their current decoding approach isn't yet optimized to run at this speed in real hardware. There are also physical challenges that simplified lab demonstrations don't fully capture yet, like atoms occasionally being lost from the array, or small errors that creep in while atoms are being physically moved around. None of this erases what's been achieved. It just means the honest answer to when will this change my life is still, we genuinely don't know yet. And anyone giving you a confident year on a calendar is guessing. What we can say with real confidence is that the direction of travel has changed. This entire wave of progress, the Chicago Blueprint, the QuEra Harvard MIT memory results, the IBM Chicago Quantum Advantage demo, didn't happen in isolation. It's part of a much larger, well-funded race. IBM has committed roughly $100 million to developing quantum-centric supercomputing in partnership with Chicago's quantum ecosystem. And Google has invested around $50 million supporting quantum research and workforce development in the same region. The University of Chicago sits at the center of the Chicago Quantum Exchange, one of the largest quantum research hubs in the world, bringing together universities, national laboratories, and industry partners all chasing pieces of this same puzzle from different angles. If you found this breakdown useful, consider subscribing, because this field is moving fast enough that what counts as cutting edge today might be old news in 6 months, and I'll be right here explaining what actually changed and what's still just hype. Here's the honest way to think about everything we've just covered. For years, quantum computing's biggest obstacle wasn't imagination, it was arithmetic. The vision was always there. The molecules we could simulate, the codes we could break, the materials we could design, all of that had been sketched out on whiteboards for decades. What was missing was a realistic path from millions of required qubits down to something an actual laboratory could build in this decade, rather than some distant one. The University of Chicago's Blueprint and the wave of research it helped unlock across QuEra, Harvard, MIT, and IBM didn't finish that journey. But it did something almost as important. It made the destination look reachable instead of theoretical, and in a field defined for so long by promises that keep sliding further into the future, that shift from someday to soon, if the engineering holds, might end up being the real story here. If you want to keep following exactly how close soon actually gets, hit that like button so more people see this, and I'll see you in the next one.